Okay, well, hello everyone. My name is Megan Carter. I'm here today as ESIP's Community Director to welcome you to the first webinar in the Earth Science Information Partners Putting Data to Work webinar series, which follows ESIP's 2020 year theme of Putting Data to Work, Building Public-Private Partnerships to Increase Resilience and Enhance the Socio-Economic Value of Data. This webinar series moves beyond data discovery to explore how the Earth Science community is putting data to work, using and reusing data in new and creative applications, creating derived products, and showcasing examples of data integration in order to enhance the resilience and the socioeconomic value of data. In addition, playing on the double meaning of the word work, this series will highlight public-private partnerships as we explore how data usage increases the value of earth science research to other economic sectors. This theme resonates very much with many of ESIP's collaboration areas, so we're collaborating with them this year to bring these webinars to you and to build connections across the community. Today, as you likely know, we've joined the ESIP Information Technology and Interoperability Committee in their regularly scheduled Tech Dive webinar slot. I'll pass it over to them in just a moment to lead the rest of the call. But just in case you're not familiar with ESIP, I'll share just 2 slides. So for more than 20 years, ESIP has helped members of the earth science data community find each other across traditional boundaries and work together. ESIP does this by fostering rich collaborative experiences, which include 2 annual in-person meetings, numerous community-driven virtual collaborations that I'll tell you about in a moment, and through the ESIP Lab, which supports the development of innovative applied earth science technologies. ESIP is funded by NASA, NOAA, and the USGS, and it currently has more than 150 partner organizations spanning the federal, private, and academic sectors, as well as many more individual participants. ESIP collaboration areas are those primarily virtual collaborations I mentioned a moment ago, of which IT&I is one of. These address pressing and emerging data-related challenges and opportunities for the benefit of science and society. These groups typically host monthly webinars with activities ranging from open discussion on key topics to webinar series to outputs like guidance documents and in-person sessions at ESIP meetings or elsewhere. You can see all of the themes and topics that the current groups convene around. You can check out the ESIP Telecon calendar on our website to see when groups are meeting, and feel free to join in at any time. No RSVP is necessary. Now I'd like to turn it over to Dave Blodgett, Chair of the IT&I Committee, to tell you more about the committee and to introduce today's speakers.
Perfect. Thank you, Megan. All right. So yeah, we've been talking about this idea to have the collaboration areas take part in the 2020 ESIP theme, and I jumped at the opportunity, and we also had a talk lined up that was pretty primo, so to make that happen. So before we get to today's talk, I just wanted to mention a couple things that are kind of guiding me in putting these talks together. And in the last few, I've encouraged people to get in touch if they have ideas for further talk, and I'll do that again. I'm very interested in hearing what's going to be relevant to the community, and I'm excited to bring these together and get them onto YouTube and whatever for perpetuity. So I guess the idea with these talks, I took this concept, I think, as much as I could from Rich Signell, who ran this group before me, is that we've got information technology and interoperability, kind of best practices, standards, all this kind of stuff that's super complicated. But the descriptions of them and our applications of them necessarily don't have to be all that complicated. And we've had a really good series of presentations that get us there. That I think we've been, I guess we've been trying to kind of follow this all along and have some really advanced and interesting presentations brought to a level that is really relatable and useful to a broad group of people. So with that, we're also working in this world of really long-term vision, but places that we can make incremental progress and have some really practical applications. And so some of the work that we've been doing recently, this slide is actually kind of explicitly to speak to some of the presentations we've had in the last little while around linked data and semantic web, and the more practical side of that, which is kind of putting that data to work in the real kind of mass market internet. So this is kind of where we are with today's talk, and I hope to continue on this kind of vein where we're looking big, we're going long, but we're also trying to get some really valuable things done near term. And just as a reminder, all of our previous talks, including a previous talk about the location index, are on YouTube. The very latest one, unfortunately, I was not able to put up, but pretty much everything else in our recent series and further back is available if you want to go back and review any of the topics. So that's the few things I had to say up front. I'll pass the screen over to our presenter and introduce. We have Irina, and no, I don't see Irina. There we go. Make presenter. All right, there you are. We have Irina and Shane from, and you'll have to do your organizational affiliation for me. I'm blanking on the organization. But
Geoscience Australia.
Yes, Geoscience Australia. And we got a really interesting talk on this idea of a discrete global grid system, and then another follow-on on the location index, and it's kind of a linked data infrastructure that starts to integrate with discrete global grid systems. And we ran out of time on both talks, and there's definitely more to cover. This is a really great project, and I was excited to have them back to give one more presentation about the real kind of application space between linked data and discrete global grid systems. And Irina had a presentation queued up on some recent, very topical work that was done in the bushfires that happened recently, or potentially even still going on. Curious to hear the latest. And yeah, so we're having them back to go one more time. And the last thing I'll mention is, well, I'll save that to the end. We have a great talk lined up for next time, and if I have time, I'll give a quick teaser on that. So without more, sorry to take away from the time, Irina and Shane, I'll let you take it away. We're still not seeing your screen. If you can push play.
Okay.
There we are. We see DGGS in action slide. Thank you so much for being here. If you want to take 30 or 40 minutes to get us to 10 to 20 minutes to go, we'll have some time for question and answer. So thank you for being here, and take it away.
Okay, so our presentation today is about one of the components of location index project, which is discrete global grid system and its application for several use cases. So I will start talking about just an update on location index and what location index project is. Quite brief presentation, our several slides. People can look at previous presentation for probably deeper information about this project, and then Shane will talk about the use cases themselves and the benefits as we see them. Right. If I can go to the next slide. So several years ago, Australian government invested in a program which is data integration partnership for Australia. And the main aim of this investment, it was to maximize government data to improve policy advice. So there are a number of different federal government agencies involved, such as Australian Bureau of Statistics, Bureau of Meteorology, Department of Health, Treasury, and Geoscience Australia, CSIRO, and a number of others. And they're trying to see how they can modernize their data holdings, the storage of data, exchange mechanisms, technology behind it. So one of the projects through this program is location index. And location index idea is how can we enable and bring together data from multiple government agencies through a reference location. And reliably, effectively, and efficiently build information framework for data exchange in a federated way without actually bringing data together. So the two main technologies we were testing is semantic web technologies, where we're transferring data into linked data format, introducing vocabularies, and also discrete global grid system engine. So what is we're experiencing currently? So it's basically quite a spaghetti ball. So how we exchange information, how information flow is recorded, it's quite inconsistent. Every time information is getting aggregated and in different ways, information is coming from different users and represented not necessarily quite consistently. And how it's being aggregated, it's not recorded. Most of the data analysts either using Excel spreadsheets or GIS systems for data integration, so they quite commonly require quite high-level technical skills. What we are aiming is to introduce a number of common APIs and data standards to streamline the whole process. So we would build a location index as a linked data metrics, which allow data analysts consistently and reliably access to up-to-date data from the authoritative data source. So they will be provided with a set of different APIs and also GUI interfaces, which allow them to access data, integrate data, and analyze data in consistent and very repeatable manner without requirement for a specialized GIS knowledge. So what we're trying to achieve, so our vision that anyone can access data everywhere and any time. And as I said, it's part of Data Integration Partnership of Australia. And the goal is to help government to create new insights into important and very complex, quite commonly policy questions through data integration and analysis. But from technical side, we're trying to create a framework which help us to introduce a consistent and extendable and seamless integration of data on people, business, and the environment to help involved agencies to solve their portfolio policy problems or sometimes cross-portfolio problems. So current partners are Australian Bureau of Statistics, Department of Agriculture, Water and Environment, Geoscience Australia and CSIRO. And J and CSIRO are leading the technical part of the work on behalf of the partners. So our major technical goal is preparedness for the future. So we're trying to bring all the technologies for the location index infrastructure to the modern era. So data is prepared for use by Internet of Things, artificial intelligence or machine learning. The architecture is flexible and easily deployable and secure. So the technical side is also looked after and modernized. And we are testing technologies to support modern data mining and integration. So semantic integration of linked data is quite important to us, and we see its number of benefits from this. So people can discover it through the web. It's enable machine-to-machine communication. It's extendable by linking to our linked data sources on the web. So while we can prepare our own APIs and our own GUI interfaces, people can access registries and use the data in any way they like, and it's suitable for them. So it can be reused beyond traditional client base and use cases openly and globally. So we have a number of pre-calculated indexes which can help people to improve efficiency of data integration if they just concerned with the data we're integrating at the moment or indexing at the moment. And it also enables this consistent data mining from multiple spatial and non-spatial data without GIS. So basically what we're trying to build is GIS without GIS through open link data applications. So what are our challenges? So for the government agencies, we actually like in reliable ways to consistently identify spatial things. So quite commonly, we don't have persistent identifiers. So one of the things we've been testing for location index is introduction of a layer of persistent identifiers and architecture around those persistent identifiers, including governance. How to link geography and observations? So we're dealing with political, socio-economic, statistical, and scientific data. Quite commonly, they are recorded in a very different ways. It could be raster, vector, tabular formats, or multiple others. So how to bring it together, how to identify linkages. Everything is happening in a place, but it's not necessarily this place is recorded consistently. Yes, so geographies which we are dealing with could be artificially organized, like statistical and administrative boundaries, or it could be geography descriptions or vector gridded data. So we're using DGGS, and we tested it on several examples, like recent bushfire data integration. We also tried to utilize it for the process we've been previously doing using traditional GIS, and also we been integrating data, raster and vector data for Digital Earth Australia. Okay. So now I'm passing it to Shane.
Thanks, Irina. So just to give a bit of a recap of what is a discrete global grid system. Essentially, there are lots of types of discrete global grids. They come in forms of rectangular, triangle, and hexagonal. What we are using in Australia at the moment is a rectangular system. It's a fixed cell hierarchy, which we quite like the fact that it's an equal area calculation over a whole world application. That means it's math-based, which means that we can program it, so we're not relying on GIS aggregations and queries. A real advantage of the discrete global grid is that it's agnostic to projections and data formats, which is making it easier for us to work in between, particularly the vector and raster environments. Oops. Cancel. Sorry. The essence of discrete global grids. As Irina highlighted before, we've been investigating persistent identifiers, and what we've found with the discrete global grid is that it provides what we call a permanent location in the Earth. And what we're calling permanent is that we don't believe we'll have a need to change this in a 10-year period. The cells are ordered and regulated. For example, we can select a level 10, which if you look to the right of the screen there, a level 10 AusPix area is around about 169 square meters, or if you like, 2.44 hectares. It's a nested table, so we're able to use parents and grandparents and child versions to scale up and down within the nested environment. We developed a linked data API and database, and this provides in the connections to the location index. The AusPix DGS engine, we use this to also recalculate work. As Irina highlighted earlier, we've done some pre-calculated indexes. For us, we've built this around the level 10, but if we need to go to a larger resolution, such as level 11 to say level 15, we can use the discrete global grid engine to calculate that on the fly. And it can be associated with raster and vector data. I want to go through quickly with 3 use cases that we've been trialling here in Australia. One is around the bushfire that recently happened in Australia over the autumn-summer period here. Just to give you a bit of a scale, these bushfires were around about 72,000 square miles, or if you like, about half of Montana or North Dakota and Delaware areas combined. Or if you want to look at it from the California wildfires in 2019, there was about 3,000 square miles burnt there. So we were dealing with quite large areas. What government needed to do quickly here was to respond and identify not just simply the burnt scars of what fires were, but also to put in place things around evacuations, planning and recovery, and support. But the challenge of coming with doing those types of things is that data integration becomes hard. In a typical GIS system, when we started to overlay the data sets, it ends up in being a very messy view. What we aimed to do with the discrete global grid was by reassigning each of the different geographies to a DGS cell, we were able to actually clean up a lot of the mess that's provided in the typical GIS sense, but also we were able to then attach statistical information from tabular data. This allowed us to aggregate the information to co-located areas. In total, we were asked to build a number of geographies within the discrete global grid, ranging from typical things like postcode areas, localities, our Commonwealth and state electorates, our national parks and reserves, state forests and crown lands, our national file address system, our ABS statistical areas and local government areas. And typically the questions that we were being asked to pull out of the discrete global grid were things like what postcodes electoral government areas and that have been affected, what was the total area of the burn area, how much burn area in my local government was national park and reserves, and how many addresses have been burnt in my suburb. What the discrete global grid allowed us to do was to essentially create a large lookup table. And if you look to the table to the top left hand, the dark blue table, this table basically allowed us to filter basically on any of the attributions that came into the discrete global grid cells. In total over this area, I think we generated around about 1.5 million cells calculated over the burnt areas. But more importantly was that because it's all maths derived, we were able to then recalculate on a weekly basis as new fire scars were being identified. So these tables were then able to be then resupplied onto other users and analysts for further use. Just to go through a couple of little examples there, we're able to quite clearly articulate through the discrete global grid calculated areas of national park burns based on hectare over each of the local government areas. And then we're able to aggregate these things up based in state examples. For example, New South Wales and Victoria were of particular interest over that period. The way the workflow was used in this case was that we were able to obtain the latest burnt areas. So we collected them by shapefiles from various agencies. We were able to convert those burnt areas into zones of DGS cells. So we were able to group them. Those cells were then linked to other information such as postcodes. We then exported out the outputs from the discrete global grid as either databases or CSV tables. And part of the workflow process was that we used a whole range of open source type coding such as Python, R, Excel, and SQL. At the end of the calculations of the DGS lookup tables, we were then able to then revisualize them back out. And in this case here over Cabargo, we were able to then provide representations of the LGA and in this case here, the addresses that were burnt. The second use case that I wanted to talk about was how we've used discrete global grids to conflate old topographic 250K sort of mapping watercourse lines with new LiDAR derived blue lines. The challenge with this project was that while LiDAR is able to extract out blue lines or streams very, very well. It lacks any data attributions. What the Tasmanian government asked us to do was it possible to actually use the discrete global grid to transfer attributions that they'd collected over a long mapping period and apply these to high resolution lines. What we did with the discrete global grid was that we were able to put both geographies of the LiDAR and the mapping streams and then calculate the relationships over a grid cell. In this case here, we didn't use level 10, we actually went down to level 11, which gave it into around about a resolution of a little bit more than 30 meters. The blue lines are the 250K streams, and the orange lines that you see on the screen are the ones from the LiDAR. Like all conflation things, nothing's ever a perfect match. And what happened as a result of conflating the attribution to the LiDAR was that obviously there is a little bit of a hit and miss rate. In some cases, the existing 250K blue lines extended past what LiDAR had been able to capture. Typical things, LiDAR was able to capture new streams that weren't captured before. And then we had the additional problem of blue lines that were captured in an old framework that didn't get picked up by the LiDAR sensor. In total, we're able to process around about 75 to 80% of the network. But what was really important to pull out of this was that this automation process only took a couple of hours to run over an area of around about 15,000 streams. In total, what we also did with the discrete global grid was that we were able to then, with Python, be able to pull out known issues that weren't able to be conflated. And that meant that we were able to then target certain cells to improve that automation process. An example of that is in and around where we have multiple stream inflows coming into a certain cell that the original level of detail wasn't able to determine what attributes should be assigned to which stream. In these cases, we then used the discrete global grid to actually drill down until we found a suitable level and then assigned the association stream to the correct stream. The next use case that we've been using the discrete global grids for has been looking at water bodies, again from a mapping environment, but looking at from comparing it to what we call our water observations from space, a program which is from our Digital Earth Australia using the 30-year Landsat archive. In this case, the problem with the satellite imagery is a similar one to what was previously highlighted with the LiDAR streams. We're getting a lot of rich information, but it lacks necessary attribution, which is known to us. In this case here, we took surface water from Queensland and we wanted to identify attribution that had been derived by AI around irrigated areas from the satellite sensors. So what this required was that we needed to actually work in between raster and vector, and this tested the raster and vector integration process. What it ended up being was that we were able to determine a many-many relationship to the map water course lines or areas with the observations from WAFs. So in summary, what ended up happening was that what comes out of the derived product from WAFs is that we end up with a persistent identifier here, but it actually lacks a lot of meaning in from the real world sense. And what they wanted to identify was, how do we actually start getting some of these other attributions such as perenniality, hierarchy, names of watercourses that are associated, and what are the feature types that rely into other data sets. What this meant was that we were able to then answer some consistent things to a range of questions. It was repeatable because it was all code. The other good thing about this project was that we were starting to look at how do we actually take big data from satellites and start linking it with the little data that we call our topographic program. But what the aim of this was that we're actually starting to turn big data into big information. Processing of this over Australia didn't take months, it took days. It really started to improve the relationship in between our raster and vector groups within Geoscience Australia. It had the good advantage of the discrete global grid is that it has no reliance on any complex schemas. It moves quite comfortably in looking at whether it's raster or vector. So in conclusion, from the work that we've been doing with DGS so far, is that what we've worked out is that the DGS defines a unique identifier. We're also looking at creating APIs over our discrete global grid engine so that we can make that more usable to users. But it also means that we can start to build these APIs within our location index framework, which means we start to take on more of the linked data process. So discrete global grids are more coming as a lookup table, and then we're looking at predefining those as linked data. Working data on grids makes it very manageable and readable. It takes away that complexity of how do we overlay layers. Cells have regular spatial characteristics. They're defined by area and neighbours, parents, etc. But the discrete global grid also has an advantage that it has topological relationships, so it can scale up and down and identify cells next to and above and below. Any data can be enabled within the discrete global grid. We've currently tested definitely the vector and raster relationships. We are starting now to move into how do we use this better with imagery, which again is just really another form of raster. Data integration products can deliver response in urgent times, and this was a good example with the bushfire example. Benefits for GA with the discrete global grid. Do you want to? Okay. First of all, from a data perspective, we see that the discrete global grid is very flexible at linking multiple data formats, types, and structures. Technically, it's quick, reliable. Because it's code-based, it can be repeatable and reusable infrastructure and codes. Probably the most benefit, though, we're seeing with the discrete global grid is the way in which we're able to start building collaboration networks. First of all, dealing with our stakeholders, being able to apply in many different use cases, but also it's starting to prove a very useful collaboration tool across governments, particularly within the location index space with CSIRO, Department of Water and Environment, Geoscience Australia, the ABS, and our Department of Industry and Innovation Sciences. But we're also starting to see more of awareness too as statistical information starts to become more interlinked with geographies, seeing that particularly coming from the Department of Health and our Indigenous Australians and our state partners, being the New South Wales Government. I'll hand back to Irina now, and she's going to talk about some more of the benefits from GA.
So for GA at the moment, and the National Location Information Branch where Shane and I are working, are looking at improving overall access to geographic type of data and linking it to scientific and other types of data from so from data perspective, we are unlocking data potential. So we're creating the new format of data, which is enabling machine-to-machine data integration, analysis, and mining, and removing needs for cross-agency data transfer. So it's quite huge advantage for us because finding data and transfer of data sometimes take up to 60% of the project time. We're obviously accelerating innovation within GA, so we're developing and testing new protocols, tools, APIs, And with testing not just for access of NGA, but cross agencies. And new technologies like linked data or semantic web and integrating it through systems like DGGS. And as Shane mentioned already, we are maximizing collaboration. So we are improving relationship between multiple sectors. So we already targeted governments at federal and jurisdictional levels, but we're also collaborating with research organization and organization like Research Australia Data Commons and universities and also industry. And as part of the project, we are developing a common governance process and workflows, and something what we currently call a special data authority.
Linking authority.
Sorry, special linking authority. So it's basically the governance body for ensuring that the location index outcomes has languidity, that the processes are following in a consistent way, and we can a way of introducing new data to the projects, and also collect and the requirements from different stakeholders and respond to their needs. So that is it. So any questions?
Muted a few people who I will unmute now in case there are questions. Well, if there are none right off the bat, I definitely, oh, go ahead, caller 3. All right, maybe not. If there are none from panelists, I'll go ahead and have you go back to where you were integrating remote sensing water bodies and your vector water bodies. That's pretty topical for some stuff that we've got going on right now, remapping our waters of the United States. And I guess in that space, how can you help me understand how finally you decide to refine the DGGS to say a DGGS cell is or isn't part of a water body, or am I maybe misreading the application?
So what we're doing there is we're taking the extensive mapped water bodies, whether they've been done from raster or vector, and then assigning a cell value to it. So what the cell value really is doing is just saying, where does information fit within a location? And that location is being defined by an equal area. So in the case of what you need to do with a discrete global grid is work out what is the level of resolution that you want to do to link location to different geographies. So what we did with the WAF data was that we didn't necessarily go right. I mean, Landsat data is around about a 30 meter pixel. We didn't necessarily always go down to a 30 meter grid cell. What we did was we looked at the grid cell of the centroid of that cell, and then seeing whether or not we can identify a water body to that centroid, essentially. If we couldn't, or we didn't get a complete match, then we went down to the next level. And then basically what we could then do is group the cells to map back to the water bodies. Does that make sense?
Yeah, I think so. So you're getting down to a scale at which you can discriminate yes or no, this cell is water. Is
That's
that
right.
Yeah.
okay?
The
And
other
that makes,
advantage of GS, Dave, is that you can use different resolution cells and
yeah,
mix and match them together. So for some, say, larger bodies, you can use larger, like one level of DGGS. For smaller bodies, you can go to the next level and then bring them together. It's just a table, so you do a query, basically.
that's yeah. I'm gonna have to think about that one a little bit. That's fascinating. Because there is this basic issue of when do you decide to represent a water body as a one-dimensional feature versus a two-dimensional feature, and in some ways this gets around that because we're always representing them as two-dimensional features, just at a finer level of granularity as they get smaller. Just interesting.
Yeah.
Dave, we have an anonymous question. This is not for me. So you
Okay.
said that this was enabled by an Australian government investment. Can you explain that a little bit more? Just interested from the perspective of a different country.
Okay. So the DEPA program, it's, from my memory, $53 million Australian dollar investment. And it's been targeting large data hubs like the Australian Bureau of Statistics or Department of Health to modernize access to this data. So so there were a number of directions with this investment. So several large data hubs were built as a result of it. Say one for business data, one for integration of statistical information with health. Then the second direction was to improve data storage and organization within departments themselves. So, for example, quite large amount of funding was provided to Department of Health for changing their storage, for improving data management of the data, and also improving data description and metadata about their data holdings. And the third direction was about how we actually can introduce new technology and build new processes for data integration. And that was commonly done through what they call PN projects, which is physical environment network projects. So that's where different government agencies were developing new mechanisms and techniques for integrating of data and also for data analysis. So location index was one of those projects.
Thank you.
Yeah. So what's happening now? All the outcomes of those investigations and projects are going to be available for common use for people. A website was developed for this through DEPA. So yeah, we hope that it will continue, and the organizations are encouraged to continue collaboration in this space. And like us, for Geoscience Australia, we found extremely beneficial for ourselves and also for improving collaboration with our partners. Hello?
We're here. I'm just leaving the line open in case anybody else has questions to pipe in. I definitely have one other, I guess, follow on to what I asked just a second ago, and that's, I guess I see with this mashup of raster and vector and refining certain things that may typically be vectors down into very small, potentially small DGGS levels or refined levels. You must end up with lookup tables essentially that have very long lists of DGGS cell identifiers for particular geographies or particular features. Is that the case? And I guess what kind of system are you using for that? Is it just a big indexed SQL database, or how is that part of the system integrated or implemented?
Yeah, I mean, at the moment, we're just using a Postgres database.
Yeah.
You're right. So what we've done at the moment is we've calculated, I guess, a whole table at a level 10 across Australia. In saying that, that's around about, I think, 1.2 billion cells. And that's fine, I think, to do if that's the level that you're going to consistently use. But what we've also done with the discrete global grid is that you can actually use the engine that calculates cells on the fly, and this is where we've started to build a linked data option around the discrete global grid. So if you wanted to define the level that you're interested in, and you knew the area that you wanted to calculate, you could generate that basically in a cache. So you wouldn't need to necessarily process the whole country all the time. That can be rather useful too, in sense, say something like the mapping water bodies, where over the whole landscape, the actual mapping of water bodies is actually fairly small compared to the rest of the landscape. So you don't necessarily have to concentrate on calculating all of the cells. You only need to calculate the cells over the areas that you're interested in.
And I guess the second advantage of this architecture which we are introducing, because it's a relational database behind the scenes, so you can apply various database techniques to improve efficiency for database interrogation, but it's also you can join your data sets as required rather than all into one humongous schema.
Yeah, that makes sense. We're jumping off into this world of multiple sources of truth, essentially, where some are fields and some are vectors, and having this unprojected refinable mesh to use as an integration point seems really advantageous. So it's interesting. I definitely have to spend some more time with this, but we have a question from Leslie. Leslie, I think you can unmute yourself if you want to ask, otherwise I can ask for you.
Yeah, she's having some logistical issues, so I think we can read it for her.
Saying, I'm wondering if you think DGGS and LOC-I is something the USGS could take advantage of for its data integration with other agencies. And well, okay, so maybe that was an interesting point you were saying, and I wonder if you can talk a little bit more about, in particular, how the DGGS has been used between agencies as an integration point.
Okay, so each organization is continuing to maintenance of their own data registers. So we basically not bringing data together, so the data can be maintained, updated regularly as required for this particular data type and in line with the processes of each organization. However, the common component that linked data index, that's where we provide the metrics of linking between different data types, so different objects or features, and also the type of the linkages between those features. So all the interrogation going through APIs and through that index. So basically the index is getting queried depending on the question, and then the attribution itself is collected through APIs from each of the agencies.
Dave,
I
what
think that
are
makes sense.
your thoughts on that? I think that question was partially for you.
Yeah, fair enough.
Oh,
I don't have a clear answer to it, and I was curious to hear more about how it was being used. It makes sense that having a unprojected spatial index that we can refine would provide that common reference point that everybody can index their content to, and we could build a registry around. Somebody does still need to own the registry, but it becomes a neutral arbiter essentially of the information. If I'm understanding how you're using kind of distributed APIs that all register into a single linked data infrastructure.
Yeah, so the governance is extremely important in this space.
Yeah.
And we are just in the process of building one at the moment. So the actually cross-agency body which can say, okay, we agree that this particular agency can take responsibility for the index, and we are going to help to maintain it, but we're taking responsibility for our own data and providing access to this data in particular format. So it's sort of quite important aspect of the whole framework.
So this is where we've decided to try and establish a spatial linking authority to oversee it.
That makes sense. I mean, it's at the end of the day, it's people are going to need to play with whatever technology you come up with.
That's right.
Yeah, and they need help. They need to understand how they can use it, what's been done so far. So it's quite an important function.
Yeah, but this technically this bridge between remote sensing or otherwise gridded coverages that are projected and precise vector representations of features. It really is a tool that allows us to kind of do that governance with a flexibility that, I think it's compelling, and it's good to see the experiment you all have taken on here being somewhat successful, or definitely successful in some of these applications. It's fantastic. So, all right, unless there are other questions, I think we can wrap, and I will mention that the next presentation I have lined up is a little bit of a pivot, so I will share my screen briefly and just say that I've got tacit agreement from Julian Chastain from Unidata to come and give a presentation on their newly developed and released Science Data Gateway, which is, if you haven't heard of science gateways, it's just a science gateway. If you haven't heard of this idea of a science gateway, it's been around and it's a thing in various domains, but not something I think we're familiar with by that term in the earth sciences. But Unidata has got an infrastructure now on Jetstream, which is kind of an NSF cloud, and has a whole slew of data available on there, and Jupyter interface to it. And I'm really excited to hear some more details about what it is, what's on there, what we can do, who can use it, all that. So that will be next month, same place, same time, very much in the theme of putting data to work. And yeah, that's it. We got a few minutes to close out, and I guess last call. Any questions for Irina and Shane? All right. Well, thank you very much. It's a great presentation. I'm sure we will be keeping tabs on what you all are up to, and hopefully we see you at another ESIP meeting before too long.
Thank you very much, Dave.
Yeah, thank you.
All right. See you, everybody.
Yeah, bye.
Bye-bye.